Okay, people joining. Stop sharing. And yeah, maybe now we can start. So good afternoon, everyone. Welcome to today's NITheP colloquium. My name is Berezhiani. I'm the interim director of NITheP. And today it is my great pleasure to introduce Professor Malik Maaza. Professor Maaza is I'm sorry, I read the whole list of titles because I don't want to make a mistake. The UNESCO, UNISA, ITLABS-NRF, Africa Chair in Nanoscience and Nanotechnology. Yeah, and just to give you a sense of the profile of Professor Maaza, he's a fellow of the African Academy of Sciences, of the Royal Society of Chemistry in London, of the National Academy of Sciences of India, of the New York Academy of Sciences, of the Islamic Academy of Sciences, of the European Academy of Sciences, and of the American Association for Advancements of Science. And so there are not many academies Professor Maaza is not a member of, and this is all testimony of his highly regarded standing in academia, and in particularly, of course, in his field of expertise, which is nanoscience and nanotechnology. And today, I'm very happy that Professor Maaza volunteered to give us a talk on neutron wave packets, wave matter interferometry of neutrons. And this is very interesting because the discovery of the neutron is almost 100 years old, and it will be very interesting to see and listen to Professor Maaza what happened recently in this very important historical topic. Before I ask, maybe Professor Maaza, if you would like to start sharing your screen, I will quickly remind people how to interact with you after or during your talk. Please use the Q&A facility that you see at the bottom of the screen, and Dr. Sinaisky that you see at the top in the among the panelists will coordinate the question and answer session. Yeah, and since and he might also allow some people to ask the questions personally to Professor Maaza. Professor Maaza, if you would like to share your screen, you just press the green button with share screen at the bottom, and yeah, and then you should.
Let me come out and come back again because I don't see that button anymore. Let me do it again, please.
I see you are probably logged in a few times.
Okay. Let me.
We tested it before we went live.
Correct.
And it worked.
Correct.
But as you, if something works live in testing, doesn't mean that it works live.
Let me. Okay.
You should have all the rights, Professor Maaza, to share the screen.
Okay, let me.
I can ask you to start. Let me try this. I ask you now to start the video. Does this make a difference?
Yes. Okay, let's hope I have started.
Okay. There's something happening. Do you see the green button, Professor Maaza?
No, okay, I'm starting it again, okay.
Yeah. Ilya, do you see the green button?
Be working now. Oh, it's okay. Share. Okay, fine. And I'm done here.
Okay.
Yeah.
Yeah, now something is happening. Fantastic. Yeah, and if you go now on slide show,
yes,
full view, yeah, then we are in business.
Okay. Sorry, I do use only one hand. So, okay.
No problem, take your time.
Is it okay now?
That's perfect, fantastic. Thank you very much.
Okay.
So, Professor Maaza, it's your show. You're welcome to start your presentation.
Thank you so much, dear Chair. First of all, I wish to express my gratitude to you and to the staff of NITheP for inviting us to share with you this recent results in effect. And I would like also to express my gratitude to all participants from South Africa and from Africa and other parts of the world for taking of their precious time and attending this seminar. So the talk of today that I would like to share with you is titled On the Peculiar Behavior of Neutrons Bio-Nanostructures. It does not, and it contains exactly the targets and the aims which were highlighted in the abstract so far. And as correctly stated by Professor Francesco Berezhiani, we are nearly at a century of the discovery of the neutron, and this talk is subscribed with that, within that framework. Sorry, allow me please to mention that the work that I will be sharing with you is done within the framework of the UNESCO, UNISA Africa Chair in Nano, and ITLABS Africa Chair in Nanosciences and Nanotechnology, which is a trilateral partnership between the UNESCO, UNISA, and ITLABS, a national facility of the National Research Foundation of South Africa. Well, I do not, how can I say, the outline of my talk consists on 6 points. The first one, if you allow me to do so, to introduce the U2ACN2 platform. Second, to give a brief overview on the historical background of the neutron, since its discovery to recent years. And I will focus on 3 typical examples, from experimental point of view, in effect, to highlight how peculiar the neutron can be. For example, to share with you that the neutron can also tunnel. The tunneling phenomena is also a characteristic of neutrons, and also to show you how a neutron can be transparent to the most highly absorbing elements, to boron, tan, to cadmium, and somehow to the xenon. And I would like to share with you what could be done in this new neutron sources, research reactors like SNS in the US and ESS in Lund.
Jamila, Gush Bey, Malik webinar dare.
Sorry? Well, I will, if you allow me, I will start by introducing the U2ACN2. As I mentioned, the U2ACN2 stands for the UNESCO, UNISA, ITLABS Africa Chair in Nanosciences and Nanotechnology. It's a trilateral partnership between the UNESCO, UNISA and ITLABS, and its mission and vision are human capital development at the level of postgrad and MSc, PhD, and postdocs of African fellows from different parts of the African continent. And recently it was expanded by the will and the wish of the UNESCO to the countries from the south. So that includes, of course, in addition to Africa, includes Latin America, Middle East, and Asia. And well, in that regard, we have received quite a number of fellows from Pakistan, from Iran, and from Bangladesh, and so on. And well, one of the major components on which we stress in terms of training of fellows from different parts of the continent and the south are the female component, in line with the SDG 5 of the Sustainable Development Goals of the United Nations. And well, in addition to the Human Capital Development Program, that is really the cornerstone, there is an additional cornerstone program that is the HCF. That is the human capital mobility of senior scientists and emerging scientists, within which we invite quite a number of fellows from different parts of the continent, in particular now extended to the south, to visit us and to spend with us scientific visits between 3 weeks to 3 months. Colleagues, I think that somebody has to switch off his microphone. It's interfering with me. Anyway, so the human capital,
I'm not sure.
The human capital mobility is dedicated for senior scientists and junior and emerging scientists, whereby, how can I say, their visits are co-funded by the UNESCO chair and partners from the north, that is the ISP, the Swedish International Science Program now, that is the DAD, the German DAD, that's the ICTP, TWAS, OWSW from Trieste in Italy, and other international partners. As a derivative of this continental dynamic and south-south dynamic, it has allowed us to target and put all our efforts in targeting and resolving a problem, a scientific problem of a huge societal impact. And by doing so, we do co-author together. For example, this is a typical publication co-authored by around 5 colleagues or 6 colleagues from 6 different institutions from 5 different countries in Africa. Sheikh Anta Diop from Senegal, Obafemi Awolowo in Nigeria, the University of Yaoundé in Cameroon, University of Roma in Lesotho, and ITLABS and the University of South Africa in South Africa. Well, today what I would like to share with you is some peculiar properties of the neutrons, and in particular the lifetime of the neutrons, and the possibility to further the science of neutrons using high power, high flux neutron research reactors. Well, in terms of history, the existence of a neutron was postulated in 1920 by Sir Rutherford, and its existence was confirmed in 1923 by Chadwick. Since then, it was demonstrated that it's sensitive to the weak and strong nuclear forces, as well as the electromagnetic, including the gravitation. And since the beginning, it was the cornerstone, one of the cornerstones of the Standard Model. And once the Enrico Fermi in 1946 has observed the total reflection of neutrons, so the wave nature of neutrons has been established and was used to advance and to confirm and validate an extensive amount of quantum mechanic wave-particle duality. And the culmination of that was the genuine, the most beautiful experiment with the neutrons is that neutron interferometry. And later by Helmut Rauch in 1973 in the Atom der Institut Österreichischen Universitäten in Wien, and later after Anton Zeilinger and Cliff Shull and Neil Brookhouse from Canada and the US tried to do a single particle neutron interferometry, but that was not really evident. Nonetheless, the neutron is a particle which has a radius of the order of a Fermi, that is 10 to minus 15. I think with 10 to minus 14. I don't use a lot this unit, but it is of that order. It's a Fermi, and its cross section is the order of 0.1 bar. I'm giving these sizes just they are very small, but when we come to the transparency of a neutron in boron, these sizes are of extreme importance. Well, as I mentioned, colleagues, I mentioned that the neutron, in terms of quark gluon nature of the neutron, it consists of two down quarks plus an up quark. They are stable under strong and electromagnetic interaction, but a weak interaction can convert a down quark in an upper quark via an emission of a virtual gauge boson, and subsequently delaying the neutron to a proton, an electron, and an antineutrino. And the lifetime of that decay is of an extreme importance in cosmology as well as for the standard model, because that lifetime of the neutron is the one which governs more or less the ratio of protons to heliums, which were created as early as the birth of the universe 13.8 billion years ago. And therefore, having a clear value of the lifetime of the neutron would either support strongly the standard model, or certainly request for its how can I say upgrade. But nonetheless, that also the scientists that pinning down the neutron lifetime would help to constrain the measurements of other subatomic particles. And in that regard, there's a huge amount of a large group colleagues from different institutions, from different countries, coming together, putting their know-how together to try to measure that time life. And there are two major techniques which were used up now is the magnetogravitational ultra-cold neutron trap, and in particular the one which was reported by Patty et al. In Science, that is in 2018, and using the how can I say the magnetogravitational ultra-cold neutron trap as it is here. The reference of the paper in Science is there. You can go through the details. What is sure is the time life that was measured is 877.7 plus minus 0.7 seconds. They take the second one, which was also used extensively, both in the US as well as in Europe, and that is what is called is the tube time flight version, within which how can I say it was shown that the time life is 885.7 plus minus 0.8 seconds, and you can see clearly there is a difference between the 800 and the 877. So it is extremely important to measure this time life of the free neutron lifetime. In that regard, what we how can I say up to now the two schools are not in agreement, and each of the team suggests that their method was more precise and so on. So it is necessary to come with a procedure which would allow to reduce this difference between the time life measured by this technique, the tube, the free tube lifetime tube, and the gravitational magnetotrap. So the idea is to use at the end of each of these setups, which are extremely complex, as you can guess. I mean, you see the setup and you see the size here for the magnetogravitational, and the complexity, how can I say, in the measurements in particular here for the photo detection in the time life tube one. So what was considered, what was suggested, and you can see, colleagues, one is published in Science and the other one in Nature. So it tells you more or less the fundamental aspect of these measurements and the number of authors and the number of institutions from where these values are coming. So it is proposed to use at the exit of one of the techniques a nanostructure, and a nanostructure in addition to not to consider only the particle, the corpuscular nature of the neutron, but its wave nature in that regard. So, well, as de Broglie said, well, a particle of a mass m, a velocity v, is associated to a quantum wave packet, which has a wavelength of lambda given by the Broglie wavelength, and in that regard, that the wave nature is not new. First of all, it was demonstrated, validated in 1946 by Enrico Fermi when he measured the total reflection, the polarization of a neutron by optically speaking by Arsène Gougassov in Kurchatov Institute in Russia in 1954, then followed by thin film interference by Meyer-Leibniz in 1962, prism deflection by Landkamer and Colloquium in 66, and the August beautiful experiment of Helmut Rauch in Vienna with the neutron interferometry, shown clearly that the neutron behave as, strictly speaking, as an electromagnetic wave, and the super-mirrors reflection of Ferenc Mézay in Berlin, Bansk in that time, in the Berlin Joint Scattering Zentrum in 1978, and the first tunneling of a neutron, which was in reflection mode only, which was measured by a Steyr, and followed by Sagnac effect by Samuel Werner in Missouri in 1985, followed by the beautiful experiment of the topological Aharonov-Bohm effect by Colella in 1993 in also Missouri, and followed by a number of certain experiments of tunneling on polarized and unpolarized neutrons, both in reflection and transmission by my team, by my colleagues and myself when I was a PhD student. Well, I would like really just to come back to the beautiful experiment of the neutron interferometry of Helmut Rauch. Colleagues, Helmut Rauch in Vienna has considered a Mach Zehnder type interferometer made by silicon type diffractometer, type of interferometer, sorry, and sending a beam of a neutron and splitting the beam in two beams and detecting it in the OH beam, and he measured with his colleagues this fantastic interference pattern of a neutron, showing clearly that neutrons behave like waves in this configuration. And because of this interferometry, all the nuclear amplitude, all the coherent, and in particular the coherent nuclear amplitudes of all the Mendeleev table have been measured by this method. So all the database of all nuclear scientists who are using any nuclear scattering length density or scattering length amplitude are due to this neutron interferometry because it's highly precise. The neutrons that we are using, well, there are different types of neutrons, of course, and the neutrons that are classified according to their energy, and the ones that we are using for this, where the optical or the wave aspect, nature or identity of neutron is seen easily or manifests itself in an exuberant manner, are called the neutrons and thermal neutrons. These are their wave, more or less, their energy. So we are working in that these neutrons here. How we make these neutrons? We make them in neutron research reactors. I'm taking the case, and of course, these are neutron research reactors, and these neutrons are they come from they are product of a fission, thermalization plus moderation. Well, I'm just showing the typical case of a neutron research reactor. This is Orphée reactor at the laboratoire Lyon-Brillouin, at the equivalent of the AEC in France. And this reactor, at the bottom of the reactor, we have quite a number of spectrometers just close to the core of the reactor. This use hyperthermal and thermal, and hot neutrons, while those who are thermalized via a deuterated wall and via carbon or hydrogen gas chambers and so on, they are moderated and thermalized. So their wavelength, I will speak in terms of wavelength or energy, their energy is between 0 and 0.0025 electron volts. That is the wavelength between around 1 angstroms to 30 angstroms if we use de Broglie equation. So these neutrons are guided towards what we call the neutron hole guide, and different wavelengths are extracted from these neutron guides to each of the spectrometers, as you can see. And at the end, also, we put, generally speaking, small angle neutron scattering. And in the case here, for the neutron reflectometer, that is the one here, where the, how can I say, the arrow points are in. These neutrons in the neutron hole guide, they are between 1 and 30 angstrom. That is an energy of 0.0 from down lower than 0.025 electron volts. These are the neutrons that we are using. Well, and once the neutron is extracted, either in a form of a white beam or a monochromatic beam, these neutrons interact with the sample, and their interaction is according to Schrödinger equation, but in the Dirac notation, the bracket is given by that, where the momentum, the wave vector is mv divided by h bar. And how can I say, if we go deep a little bit, at the beginning, we consider that the neutron is interacting with a single point localized nuclei according to the Fermi potential, which is given by that. So the Schrödinger equation is written in such a way. What we do, we modify it because we are interested by the wave nature of the neutron. So therefore, we will rewrite this equation. Instead of the Schrödinger, we put it in the form of Helmholtz optical equation, where the chi-r here is the wave vector dependent of the medium, in the medium. And if we can also rewrite it in a beautiful way, still in the Helmholtz, but dividing everything by k, by the wave vector, by the wave vector in the vacuum, we will get the refractive index. And the refractive index is given by that formula, simple formula, as you can see. And how can I say? We can approximate it. Sorry, colleagues. sorry, colleagues. So the refractive index can be written in this form here, because we will be averaging the potential, the Fermi potential, and once we average it, the refractive index is written in such a form. And because V here is of the order 10 to minus 5, so V over E is around 10 to minus 6 to 2 minus 7. So therefore we can approximate in such a form that refractive index. And therefore, colleagues, what does it mean here? That means that the interaction of a neutron with the medium can be approximated as if the medium is continuous, and as if the neutron is described by a refractive index of the medium as a continuous, and that refractive index is n. So the wave packet of the neutron wave packet sees the medium no more as a single scattering point, no more a delta here, no more, but as a continuum medium with an average potential, with an average Fermi potential, and which brings it to a refractive index of n equal to 1 minus delta. Because this delta is small, therefore refractive index is equal to 1, is close to 1. So if you want to see according to Fermi and this formula, this beautiful simple formula, if you want to see the wave nature of the neutron, you must impinge the samples under grazing incidence, because the refractive index is close to 1 of the medium, any medium. Therefore, you come under grazing incidence. Grazing incidence means that the beam impinges the sample with an angle less than 2 degrees. Therefore, you need a high collimation, a high quality, geometrical quality beam, and so on. But the point is here, colleagues, and I stress on it because it's the basic of everything after. The refractive index here, the interaction of the wave packet of the neutron can no more describe it by a single scattering centers, but an average medium which has a refractive index n. So the wave packet, if the neutron sees the single scattering centers, the wave packet sees the medium as an average with a refractive index n. And that n, tip a little bit, if you go further, you will find out that refractive index, you can express it under such a form, which was derived by Enrico Fermi himself and others after. What is sure is that there is a real part and an imaginary part, and the real part depends on B as well as the sigma r here. It depends on B. The same thing for this part here. B is the coherent nuclear scattering length. It is, repeat please myself, this is extremely important. The B here is the coherent nuclear amplitude, scattering amplitude. Well, and this parameter, by contrast to light and to X-rays and so on, that coherent scattering length, which is given in a Fermi, it changes in an irregular way with atomic number or with the Z. While with the X-rays, it goes proportional. For the neutrons, no, it's, how can I say, it's really statistically, it changes in a statistical way. One, second, that this scattering length can be positive for the bulk of materials and for some isotopes, but it can be negative for some of them. When the scattering length is negative, that means the medium, the material, is transparent to neutrons, as if that medium is a vacuum, and the neutrons, they go through. Those who have a positive coherent scattering length amplitude that means this material do reflect the beam. They do not allow it to, they reflect it. If they can transmit a little bit, but not much. They reflect extensively. And higher is B, higher is the value of B, higher is the reflection of this material. Some materials, for example, are this, like a dysprosium, they have a higher scattering, coherent scattering length, but they have a huge absorption cross section. So we avoid them. We should not take them. So the ideal material is nickel for neutron optics. It's nickel. It's easy. It has quite a large number of isotopes, and its isotope nickel 58 is by far the highest reflector possible. But well, allow me just to come back to the titanium and to the vanadium. They have a negative, how can I say? They have a negative coherent scattering length. That means they are transparent to neutrons. And the nickel is, it has a positive one, but the nickel 58 has the highest coherent scattering length. So that means if we want to reflect neutrons, we have to use the, one of these nickels here, either the natural or the isotope. In effect, the natural has a large amount of the isotope 58. And for the transparent one, we should use either titanium or vanadium or manganese. See, the vanadium is somewhere here, manganese or the titanium. That is said, colleagues. Well, by neutron interferometry, a large amount of all, if you wish, all the neutron scattering lengths and cross-section of the elements of their isotopes were determined by neutron interferometry in Vienna or in Missouri. So, and using the wave nature of neutrons. So all data that the nuclear scientists use are based on this database. So just to show, highlight how important, or how was important the wave particle of the neutron interferometry, and therefore the wave particle of neutrons. That brings me, colleagues, to the Fermi total reflection. Fermi in 1946, when he was designing the first neutron beam for condensed matter, he showed that in effect the refractive index is close to 1, if you remember, for materials, for the bulk of materials in neutrons, in neutron optics. And he has shown that, well, if the material is not an absorber, that material will reflect. First of all, allow me, colleagues, to remind ourselves that because the refractive index of materials is close to 1, therefore Fermi and his colleagues deduced that if you want to do or observe or to run an experiment to see the wave nature of neutrons in a standard way, you are obliged to attack the slab of your film, of your sample, under grazing incidence theta I smaller than 2 degrees. The ideal is 1 degree or 0.5 degrees, half of a degree. Here you will be able indeed to see a reflected beam and a transmitted beam. And depending on the value of the angle theta or the wavelength, either all the beam will be fully reflected, or a part of it will be, or a full of it will be transmitted, or some of it will be reflected and some of it will be transmitted. In some cases where he wanted to see total reflection, which means I send 100 wave packets of neutrons and I have to measure 100 wave packets of neutrons, and therefore that angle here is called critical angle. Or because we can change either the angle and fix with the wavelength, or change the wavelength and fix the angle, the time of flight, if you wish. Sorry. So in the case of total reflection, what we should have the beam should impinge the sample under grazing incidence. If it is the case, so there will be a smaller reflection and until a certain angle theta c, critical angle that we call, and suddenly from that critical angle, the beam will be fully reflected, totally reflected. You send 1,000,000, 100 or 1,000 of neutron wave packets, you will detect the same number. So that is we call the total reflection plateau, and this one is the vitreous region. Now, what happens is that, and this total reflection is at the origin of all modern research reactors, all of them, being it in Europe, being it in Russia, or in the USA or Japan, all of them, they use this neutron total reflection using these neutron waveguides, like a fiber in effect, like a fiber optic for light, a total reflection. We use exactly the same thing using the total reflection phenomena discovered by Fermi. So, but we would show that this total reflection cannot be everywhere, and that the condition of of Fermi geometry or total reflection can be biased, can be circumambulated somehow, if we consider what we call Fabry-Perot optical resonator. What is this Fabry-Perot? Fabry-Perot, you know it very well. All of us, we have done optical trainings, and it tells you if you have two reflectors, high reflectors, separated by transparent medium, if you take these two highly reflecting materials separated by transparent material, and if the thickness of the reflectors and the transparent medium separating the two reflecting materials, if it is governed by this equation, that it will tell you if this condition is more or less verified, the total reflection will take place fine, but when you reach this condition, the neutron wave packet will tunnel. Even if you are in the total condition, in total reflection condition, now this neutron wave packet, if it checks this equation, it will tunnel. And if it will tunnel, you will see it in the transmitted beam, and you will not see it in the reflected beam. Well, quantum mechanic wise, that means simply that if I send my wave packet of neutrons, it is a high reflecting material, so that potential is high. It does not, it will bounce back. And here, if I take such a kind of material, but if I play on the conditions of these thicknesses and so on, and the refractive index of the materials, I will be able to have a tunneling. Yes, the neutron will not jump the potential, but it will go, it will tunnel. And if it tunnels, that means it's a wave part, it's a wave packet. Well, let's see, as St. Thomas, we believe what we see. Poof. Here we take, a Fabry-Perot resonator, or a resonator consisting of a nickel, as Fermi has done. We take another nickel here, and separating these two nickel layers with the transparent medium. It happened that in neutrons we are in the right condition within which we have materials which are transparent to them, and we have materials which are highly reflecting. Nickel has more than 80%, I think, or at least 70%, if I am not wrong, of nickel 58, and the nickel 58 has the highest coherent scattering length amplitude. Therefore, we are the neutron wave packet should be totally reflected, but in some conditions of angle and thicknesses, it will tunnel. Okay, so we have made that, and we run an experiment at the reactor Orphée. So what we measure the reflection versus the wavelength, because we use time of flight technique. So we have a white beam, different wavelengths, and we, how can I say, we impinge the Fabry-Perot nanostructure of 1,000 angstrom nickel, 1,000 angstrom nickel separated by 200 vanadium. Sorry, I done a mistake here. Sorry, it is 200 angstrom nickel, 200 angstrom nickel separated by 1,000 vanadium, natural vanadium. So we attack this Fabry-Perot under fixed angle. As you can see, 0.5 degree. Normally, all will be totally reflected, which is indeed the case. Here we have quite a nice total reflection, but we can see that in the total reflection, not all the neutrons are reflected totally. These ones are not reflected totally. These ones are not reflected totally. These ones, yes, within the background, of course, bar error. The same thing for these ones. So what does it mean? That means that if there are dips in the reflectometry or reflectivity profile, which is this one, colleagues, there are dips. That means these dips, this neutron corresponding to these wavelengths have tunneled. And therefore, how can I say? And therefore, these neutron have behaved as if they are wave packets. And if they have tunneled, therefore, which means that we will observe them at the transmission, at the transmitted beam. Yes, correct. This is the profile of the transmitted beam, colleagues. And as you can see, there are peaks in the transmitted beam. Remember, here is a neutron research reactor, which has a flux. It's a 14 megawatt type neutron research reactor. It's not 10 to 18 like the ESS or SNS, 10 to 17 neutron per centimeter square at the sample. So we have quite a large bar errors. Nonetheless, we have these dips here clearly in the total reflection plateau, and we have the corresponding peaks to these dips in the transmitted beam. Therefore, yes, we can confirm without any discussion, and as St. Thomas, we believe what we see. The neutrons who have not been totally reflected have tunneled, and in the tunneling they have been transmitted. And the point is not only that these neutrons have tunneled and therefore they behaved like wave packets. It's not of an importance here. The importance is that from the width at half maximum of these dips, we can estimate how long time the neutron has spent in the resonator. And therefore, yes, correct, because these resonances, before being transmitted, they have had to spend some time. What is that time? So, how can I say, how many times the neutrons which were transmitted through this dip, how many times have they bounced on the reflectors, the nickel reflectors within the natural vanadium spacer? How many times? If that, how is how long time they spend in the resonator? And therefore we have to go to Her Excellency, the Heisenberg uncertainty, and we use the Heisenberg uncertainty relating the delta lambda, the delta K or delta lambda here to the time. And we indeed, for each of the resonances, we have the time. As you can see, we deduce the time that the neutron has spent inside the resonator. As you can see, it's from between 0.16 milliseconds to nearly 1 millisecond. It's not high, it's not much, but the point is, if you remember the previous, the magnetogravitational ultra-cold neutron trap and the tube free lifetime free neutron tube experiment, the bar error is 0.7. So here the precision is by magnitudes higher. So we are intending to propose to the colleagues in the US and ILL, and certainly the colleagues at ESS, when their neutron reflectometer will be operational, to use these, how can I say, additional nanostructure at the end of one of the two setups, either the gravitational trap, UCN trap, or the tube lifetime measurements, to combine that at the end, a nanostructure type, ideal one to measure with a high precision the lifetime of the neutron. But what I have mentioned is just the beginning. Because with the neutron we can play far better. As you can see, if we have a high flux as the SNS and the ESS in the US and in Lund, with the flux of 10 to 18 instead of 10 to 11, 10 to 12 to Orphée, we are somewhere here. Then the resolution will be far better in terms of this bar error, and also in terms of reaching for very high wavelengths, very cold neutrons. This is what Steyr has done at the beginning at ILL, but unfortunately the bar is very high. And well, it's better, of course, to have very sharp dips to measure, to have higher precision somehow on the neutron lifetime. Well, as I mentioned at the beginning, the nanostructure itself is not intended to measure the lifetime of the neutron, but to be added for one of the techniques that I mentioned before, to have a higher precision. And in addition to that, we can play on the spin of the neutron. We carried exactly the same thing on with the spin up and spin down with polarized neutrons, where now the Fabry-Perot condition is it does change and consider the spin of the neutrons. And also the beauty of the neutrons is that we can play on the isotopes. Here it's a student, an MSc student, who retreated the data that I have had a long time ago, and well, he got his master cum laude, and whereby we clearly see also this resonances is a very nice isotopical effect, Fabry-Perot based. So with the neutron, it is really possible, and with this new neutron sources, it is believed that we could really, can I say, reach a far better precision on the neutron lifetime. And I included a number of references of these neutron optics, and that will bring me to the second and the last example that I would like to share with you. Francesco, am I in time, please?
Malik, you have probably around 5 minutes.
Okay, I will speed then. Well, what I would like, and I will send this PDF transparency to you, please, so you can share it with the participants. What I would like to share, colleagues, here is just something equivalent, whereby we send the beam, a neutron beam, on a highly absorbing medium. And that medium normally would not reflect the neutron, but it will absorb it. Therefore, we will not have any reflection nor transmission. But no, it is wrong. No, nanostructure, in particular boron, we can make the boron reflecting slightly the neutron and transmitting it without absorbing it, as if the boron is completely transparent to the neutrons. And for such as an example, we take boron. We take a boron, natural boron, but we take in effect the boron carbide, within which the boron contains 20% of boron 10, which is a highly absorbing of material that is used for, how can I say, as you can see here, this is the cross section of the boron relatively to others. We can use boron because it's easy, because the boron carbide targets are easy. So in this case, we use what we take that resonator that we have seen at the beginning, and we will duplicate it. We have here, but instead to have a reflector material, we have absorbing material, boron carbide, titanium, boron carbide, titanium, boron carbide, titanium, and so on and so on. So what we do is we take, instead the reflector, we take a highly absorbing material. We take the same resonator as before, but except we are replacing the highly absorbing material by the highly reflecting material by a highly absorbing material, and we multiply that resonator. But we will not take, how can I say, we take this thickness in a way that, and this material is a boron carbide. The black material here is a boron carbide containing 20% of boron 10, which is highly absorbing. Cross section is 200 nearly bonds. So, but what we do is that we take a geometry in which this neutron wave packets will resonate. And for such, what we do is that we take thicknesses of the boron carbide or the boron here and the titanium according to what we call Zeldovich-Vinogradov equation. And if we do so, this boron here will be transparent to neutrons. Okay, so the thicknesses that we find for this Zeldovich-Vinogradov is that the boron here layer should be 2 nanometers, that is 200 angstroms, 20 angstroms, and the titanium is 12 nanometers. But remember, we will attack this thin film here of boron carbide or boron, if you wish, by an angle of 1 degree. That means 10 to this angle is 10 to minus 2 radiant. Therefore, the neutron, in effect, it will not see a thickness of 2 nanometers. No, it will see a thickness of 2 nanometers divided by 100, 10 to by 10 to minus 2. Therefore, it will see an effective thickness, or it will travel a thickness of 200 nanometers. That is 10 to 5 Fermi. The neutron has a size of a Fermi. Therefore, colleagues understand that if we consider the single particle nature of the neutron has no chance at all with its size of 1 Fermi. It will have a high probability that it will be absorbed by a length of boron carbide or boron of around 10 to 5 Fermis. It can't be, but no, it is incorrect. It works, because if you take that neutron wave packet, it will, how can I say, if you do the experiment, it will give you what we call a Bragg peak. This Bragg peak here, this Bragg peak here, in effect, it's given by the reflection of this wave packet by these interfaces here. Each interface between the vacuum and the boron, between the titanium and the boron carbide, between the titanium boron carbide, and so on and so on. All these partial reflection will interfere and give you the Bragg peak. And you see it. This is the experimental one. So we cannot deny. This is the experimental one here. I will take this one better. Here, this is the experimental one. That tells you the beam has been reflected by these interferences, but these beams here, and it has, how can I say, they reflected, they interfered between them in a positive way, and therefore that means if they have done, that means the neutron wave packet has been reflected slightly at the top, and after the second, the third, the fourth, and so on, until the bottom. And it has been reflected at each interface, and they have interfered between them, and he gave you the Bragg peak, the experimental one, that is the Laue diffraction type. So no discussion. In addition to that, colleagues, if you see, there are small fringes here. There are small fringes that we call the Kiesig fringes. And these Kiesig fringes are given by the interference between the partial beam reflected at the interface here, at the first interface R sample, and this beam here, which is reflected by the substrate multilayer here. So these two beams have interfered between them to give birth to these Kiesig fringes, and that means if you have these Kiesig fringes, that means this wave packet, this neutron, has reached the bottom, which was reflected by the substrate, and here, and it has interfered with this wave packet to give you these Kiesig fringes, and this is undeniable here. There is no discussion for it. And therefore, that means that the neutron wave packet not only went through, how can I say, the boron carbide at the beginning in the initial beam by, how can I say, by tunneling, as we have seen, because it has tunneled through the boron carbide, which contains 20% of boron 10. That means the boron 10 was transparent for them, and they have reached the bottom here of the substrate, and again that wave packet went through and tunneled through again through all the boron carbide layers to reach the top surface here and to interfere with the initial one to give you the Kiesig fringes. And there, to explain this phenomena is in Zeldovich-Vinogradov. That means, how can I say, that means that the stationary wave during the wave propagation in the film here, in the multilayer of the wave packet, is that the minima of the stationary waves, the minima of them correspond exactly with the absorbing layer, while the maxima correspond to the transparent layer. So therefore, there is nothing to absorb in the, how can I say, in the absorbing layer. And therefore, in terms of probability of the wave function has a high probability to be maximum at the mid of the transparent layer and the minimum in the absorbing layer. That is why we observed the Bragg peak and the diffraction peak. And these colleagues, these are, how can I say, experimental results. And well, you may say, well, can we increase the number of the absorbing material? Yes, we increase it. If we increase it, then it works. Instead, the 9 layers, 9 bilayers, 9 resonators, we go for 25 and for 50 resonators, and it works. Higher is the number of resonator, better is the measurements, better is the transparency of the neutron for the high orders of Bragg peaks. So that means here the boron carbide or the boron, and hopefully we are intending to do it for other absorbing element, are transparent for neutrons in such a wave nature of the neutrons. And I think, colleagues, I would stop at that level, and here are some references in which we have published this work, and others where colleagues have cited this work that we have done. In effect, we have published this work in a journal of not a high reputation or a high impact factor, but when colleagues from Oak Ridge contacted us about this work, we understood that it's really a very a specific interest when it comes to time life of the neutron. And I thank you, colleagues.
Thank you very much, Malik, for the very interesting overview of the physics of the neutron in a in a historical perspective, from the very origins to the latest results that have an African touch. Thank you so much. Ilya, are there questions for Professor Malik?
I think so far there is none, because probably people need to have a couple of minutes to think about. Okay, now they're coming. Okay, so there is a question from Martin Buchler. I think I can let him talk.
Yes, please.
Okay. Hi, Martin. You can unmute yourself and you can ask your questions by yourself.
Hi. Thank you for a really nice talk. I have two questions. The first one is how smooth do the surfaces have to be prepared for the experiments that you described? And the second question is something I've always wondered about neutron scattering cross sections. So there's certain nuclides like gadolinium-157, which have a huge absorption cross section. So I look up 250,000 barns, and I presume that this is from a resonance, and because a neutron is so small with just a single partial wave. But the elastic cross section is tiny, and it would sort of seem that they would be comparable. You know, if you absorb completely, you sort of get a shadow. So how does one understand this? So those are my two questions. Thanks a lot.
Thank you so much, Martin. First of all, thank you so much in pointing the importance of roughnesses, because you are under grazing incidence. Not only the thin films or the surfaces have to be of an optical quality, which means lambda over 10 or 100, 1,000 even, but because you are working under grazing incidence, the films must be really very, very smooth, extremely smooth. The roughness must be less than, less than 5 angstroms. And that's why highly polished substrate, such as the silicon, for example, silicon wafers, or boron type substrate, borosilicate type, the substrate, the glass substrate, we have to polish them in a way to have roughnesses around about 5 angstroms, that is 1 or 2 atoms. And the second question is that you are right. In the case of gadolinium, a huge cross-section, huge absorption cross-section. But and that is exactly the system that we are tackling to do, is to use, not to use the gadolinium-155 or 157, but to use a multi-layer of gadolinium titanium in the, in the geometry that I have mentioned. That is the Vinogradov-Zeldovich, whereby the gadolinium layers thickness and the transparent material, the titanium, would follow the Vinogradov-Zeldovich transcendental equation. In that regard, whatever the cross-section is, there would be still a transparency. So we want really to go further and test the case of the gadolinium titanium. So the response is, we have to be in Vinogradov-Zeldovich conditions. If the thicknesses are controllable at that level that Zeldovich-Vinogradov equation tells us, and for such, there is only one place in France, which is capable to do such a high quality resonator or multi-layers. In fact, this institution does the bulk of the work for NASA, for example. And this is the one that I hope would help us in making such a high quality samples to access the ESS in Lund. But I will be delighted to kind of follow up the discussion with you and find out how we can work together.
Okay, thank you very much.
Ilya?
Okay, I don't see any more active questions, and participants are welcome to raise their hand if they would like to ask their question in person.
And maybe while the participants think about the questions, Malik, where do you see the next breakthroughs in neutron physics coming? Because you mentioned at the very beginning that one of the amazing thing of neutrons is that they are susceptible to all the four fundamental forces. So what do you expect to be the next big neutron physics thing?
I think I must say, first of all, what we have discussed today is something bringing the high energy physics to nanoscience. It's bringing cosmology to nanosciences. And the lifetime, first of all, the gluon quark nature of the neutron. You can see clearly here, we don't see that. In this type of experiments, we don't see the quark gluonic signature.
Mm-hmm.
And I think that neutron interferometry and neutron optics could really play a role in that regard, because if we could use neutron interferometry to probe the inner constituency of the neutron, I mean, to see if possible to make interferometry with the quarks. Can I do how can I say interferometry because between two quarks? Why not? Why not? They are a fundamental particle. What stops us to? An electron does interfere, electron diffraction. A neutron does interfere, neutron diffraction. Why not a quark? Why not? We should think about making quarks interfering between them. And here, I must admit, in addition to that, you have quark up and quark down. I mean, in neutron, you have spin up and spin down. We should really, I must say, because this type of experiments bring material science, bring physics, chemistry, life science, and others. In particular here, it brings really the fundamental aspect of science. Why can't we think about the possibility to make a quark up and down the equivalent of Zeeman effect, for example? Why not with the quarks? Why not? I am not an expert in this field, but I do suspect there is no limit for how can I say, for imagination. If remember, how can I say, when how can I say when the electron diffraction was observed, or when what's his name, de Broglie came with his equation. Well, first of all, he was a historian. He was not a quantum mechanic man. He was a historian by training, and he was the one who saw there are two schools against each other. The one who sees that the momentum is Ashbach K, and the other one, they see the momentum is equal to the momentum is mv, and he has had the guts to say mv is equal to h bar k. I'm not telling that I am Louis de Broglie, certainly not. No, please. But the point is that can't we think about the possibility to do interference with the quarks and to push it a little bit and to do interferometry to observe a Zeeman type effect with a quark up and quark down. Of course, this would require high machinery like CERN and so on. But, well, I think accelerator sciences is bringing us at a level where it is possible to run such kind of experiments. And well, but the most important, the most urgent one is really the lifetime of the neutron. This is really a breakthrough. It's really a breakthrough. And I hope that, how can I say, theoretician and experimentalists would come together and to achieve such challenge.
Malik, thank you very much for this exciting outlook in the future of neutron physics. I'm just worried now a little bit about the time because we went a little bit overboard. And I think we will use now this moment to thank you again for your fantastic talk and this really nice overview that I think everybody enjoyed very much. And if participants come up with further questions, they're welcome to email me or you directly, and we will make a plan to share the answers. So Malik, yeah, please.
Thank you. Sorry, I will send you the PowerPoint in a PDF, and you can share it with all the participants if you wish.
Yeah, thank you very much. That's very kind of you. We will make it accessible. So also a big thank you to the participants for being so loyal to the NITheP Colloquium series. And probably either later today or tomorrow morning latest, the announcement for the next Colloquium will reach you. So Professor Maaza, thank you very much again for a very nice talk. And we are looking forward to keep interacting with you on this very exciting topic. And Ilya, thank you very much to you as well. Yeah. So good evening.
Thank you so much.
Thank you.
Thank you so much, colleagues. Bye-bye.
And we will see you again next Monday. Thank you.
Yes.
Bye-bye. Bye-bye.
Thank you. Bye-bye.